Hello everyone, and welcome to Dr. Carminati's YouTube channel. I'm thrilled to have you here today as we explore a fascinating and cutting-edge topic. What is quantum decoupling and how is it used? If you're curious about the quantum world and how it's shaping the future of technology, you've landed in the right spot. I'd love to hear your thoughts. Drop your comments below, suggest ideas for future videos, give this video a like, and hit that subscribe button to join our growing community of explorers. Let's dive into the quantum realm and uncover the power of quantum decoupling together. Before we tackle quantum decoupling, let's set the stage with a glimpse into the quantum world. Quantum mechanics rules the behavior of the universe's tiniest building blocks, atoms, electrons, and photons. Unlike the everyday world, where objects follow predictable patterns, the quantum realm thrives on surprises. Particles can exist in multiple states simultaneously, a phenomenon we call superposition. They can also link their fates through entanglement, meaning their states connect across vast distances. These quirks make quantum systems incredibly powerful, yet fragile, as they react to even the slightest nudge from their surroundings. In quantum computing, we rely on qubits, quantum bits, that differ from the bits in your laptop. Thanks to superposition, qubits can represent 0, 1, or both at once. This ability lets quantum computers tackle complex problems faster than classical machines. But here's the catch: qubits are sensitive. Unwanted interactions with their environment, known as decoherence, disrupt their states and introduce errors. Quantum decoupling steps in as a hero, shielding qubits from these disturbances and unlocking the true potential of quantum technology. Quantum decoupling shields quantum systems, like qubits, from unwanted interactions that threaten their stability. Picture it as a protective barrier for quantum information. In the quantum world, particles constantly bump into their environment. Other particles, magnetic fields, or stray photons. These encounters scramble the delicate quantum states we need for computing or communication, leading to errors or lost data. To grasp how decoupling works, let's try an analogy. Imagine listening to a soft conversation in a bustling, noisy room. The chatter drowns out the words you want to hear. Now slip on noise-canceling headphones. They block the distractions, letting you focus on the conversation. Quantum decoupling mirrors this. It cancels the noise of unwanted interactions, preserving the quantum system's clarity. Here's the technical scoop. Quantum decoupling applies a series of precisely timed pulses or adjustments to the quantum system. These pulses tweak the system's parameters to neutralize the unwanted interactions, making them cancel each other out. Think of it like spinning a top so fast that outside forces can't tip it over. This process stabilizes the quantum information, keeping it intact and reliable for longer. Let's explore the mechanics of quantum decoupling more closely. The technique hinges on dynamical decoupling, which uses sequences of control pulses, rapid flips or rotations applied to qubits. These pulses counteract environmental effects with pinpoint timing. Picture a spinning top wobbling under external pressure. You steady its spin if you nudge it periodically with just the right force. In quantum terms, the control pulses adjust the qubit state so that unwanted interactions average to 0 over time. This preserves the qubit's original condition. One well-known method, the Carpenter-Maboom-Gill CPMG sequence, originated in nuclear magnetic resonance (NMR) spectroscopy. Quantum computing adapts similar sequences to protect qubits from decoherence. These pulses extend the coherence time, the window during which a qubit holds its quantum state, making computations more dependable. Quantum decoupling doesn't stop at single qubits. It also prevents multiple qubits from interfering with each other. In a quantum system, qubits can unintentionally tangle, causing errors. Decoupling suppresses these interactions, ensuring each qubit performs its role without meddling with its neighbors. Quantum decoupling anchors the reliability of quantum technologies. Without it, the fragility of quantum states would cripple quantum computers, communication systems, and sensors. Let's unpack its significance. Preserving quantum information drives success in quantum computing. Quantum algorithms leverage superposition and entanglement to solve problems quickly. But if qubits lose their properties too fast due to decoherence, results falter. Decoupling stretches coherence time, enabling longer, more accurate computations. In quantum communication, decoupling safeguards quantum states during transit. Take quantum key distribution, QKD, which secures communication channels. Photons carrying quantum states travel through cables or air, facing environmental noise. Decoupling shields these photons, ensuring secure, dependable transmissions. Decoupling boosts precision in quantum sensing. Quantum sensors detect minute changes, like shifts in magnetic fields or temperature, with unmatched sensitivity. By blocking unwanted interactions, decoupling sharpens these measurements, advancing fields like medical imaging, navigation, and physics research. Quantum decoupling powers real technologies and research today. Let's spotlight some standout uses. In quantum error correction, decoupling teams up with error correction codes. While decoupling reduces errors, codes fix those that slip through. This duo underpins fault-tolerant quantum computing, a must for scaling quantum machines to tackle real-world challenges. In quantum simulation, decoupling stabilizes systems that mimic complex phenomena. Scientists simulate molecules or materials too tricky for classical computers, aiding quantum chemistry, drug design, and materials science. Decoupling keeps these simulations accurate and reliable. In quantum metrology, decoupling refines measurements. Atomic clocks, for instance, rely on quantum states to keep ultra-precise time. Decoupling shields these states from noise, supporting GPS, telecommunications, and tests of fundamental physics. Even in quantum biology, decoupling shines. Researchers probe quantum effects, like tunneling or coherence, in processes like photosynthesis or bird navigation. Decoupling lets scientists study these fragile effects, potentially revealing new insights into life's mysteries. Quantum decoupling delivers big wins, but challenges linger. Applying pulses demands exact control over quantum systems, a tough feat. Timing and strength must align perfectly, or the pulses could spark new errors. As quantum systems scale up, maintaining this precision grows harder. Decoupling also requires customization. Different systems face unique noise profiles, so researchers tailor strategies for each case. This demands deep knowledge of the system and its surroundings, making decoupling a complex art. Looking forward, better quantum hardware and control methods will streamline decoupling. As quantum tech evolves, decoupling will cement its role as a key tool, building robust, error-resistant devices. Want to explore more? Dive into quantum computation and quantum information by Nielsen and Chuang, or check out online lectures from MIT or Stanford. Track breakthroughs from quantum leaders like IBM, Google, or innovative startups. The quantum frontier awaits. Keep digging. What an incredible journey we've shared today. We've unraveled what quantum decoupling is and how it is used, discovering how it protects quantum systems and fuels progress in computing, communication, and beyond. I hope this ignites your curiosity about the quantum world. What amazes you most? Got questions? Share them in the comments. I read every one. Suggest topics for our next adventure. Hit that like button and subscribe to stay on the cutting edge with me. Thanks for watching, and I'll see you soon.